Hey everybody, welcome back to another round of engineering, and yeah, let's keep going. As promised, I said that we would work on some extra examples of applying Kirchhoff's laws, so that's what I just anticipate running through for this video and possibly even the next one, just to get us some more practice, some more familiarity with it. So, that being said, let's go ahead. I just, drew up a couple of extra circuits, so we'll just start. I will draw this circuit, and why don't we go ahead and, sorry, I'm hand sticking a little bit there. We'll go ahead, let's put a resistor in right here. In fact, let's start off with a 2-battery circuit. Just make life interesting. And let's go ahead and put another resistor down here, and we'll finish that off. We'll call this a 12-volt battery. We'll call this a 9-volt battery. Let's say 1 ohm here and 3 ohms here. Okay. Go ahead. I gave you a list of applying Kirchhoff's laws. Pause the video for a second, see if you can hack your way through it. Good. Sweet. Let's go at it. So one of the things that we need to be thinking about are the number of essential branches, which requires us to think about the number of essential nodes. So I'll go ahead and let's go ahead and highlight. There is one essential node right there. And I'll do it in orange. And we have a second essential node that is essentially this whole rigmarole. Right, that is all a single node. Okay, and so we notice that due to those 2 essential nodes, we have 3 essential branches. I'll put essential nodes is equal to 2, and essential branches is 3. So we have 3 unknown currents. Okay. So let's go ahead and draw those in. And now at this point, we have to guess. Right? We can arbitrarily guess which direction the currents are. So I will go ahead and let's say that here is I1. Actually, yeah, I'll call that I1. I'll call this one I2, the center branch, I2. And for kicks, I guess we'll call this one I3. I3. And again, it's always good to label these on your figure itself. So now we have a presumed direction for each of the currents, and based on that presumed direction, we'll go ahead and label the high and low sides of the resistors. Again, I said that your choice does not matter so long as you remain consistent through the entire process. I'll go ahead and also label the batteries just so that we have everything. And you can see, first of all, it's nice to use as much of the page as possible, but also if you have different colors available, that also helps out. It's not by accident that I have a kind of case of different color pens sitting right here. Oops, there goes one. And those just come in handy from time to time. So, okay, well now we're at a situation where we can start thinking about writing our equations. And we've done all of our circuit setup. Now we're ready to start our equations. And as I recommended last time, starting off with Kirchhoff's current law, just because the equations are slightly simpler. They don't involve the resistances. And since we have 2 essential nodes, we know that we can write one equation. We can use junctions or essential nodes to write one equation via Kirchhoff's current law. So let's go ahead and write that down. I'll go ahead and choose the yellow essential node, the left one. And so I see that I have no currents actually going into that node. So I'll put 0 currents going into that node. And I have all 3 currents going out, I1 plus I2 plus I3. So we recognize immediately that one of these currents is going to have to be negative. I know I chose a wrong direction somewhere. Not surprising. Okay, well, now that we've used up all of our possible junctions or essential nodes, we need to progress on to Kirchhoff's voltage law, KVL. And I don't know, this is a fielder's choice. We'll go ahead and start off with cyan. I'll go ahead and I will use the bottom mesh and the top mesh. Okay. So I like thinking in terms of meshes just because there's no reason really, I guess. And okay, so, and I'll still go clockwise here. So I'll go clockwise on the bottom mesh and I'll go clockwise on the top mesh. So, of course, you can pause right down the video, or you've already got this solved, so I'm just reaffirming your solution here. So let's go ahead. Walking around clockwise, I see a drop across the 12-volt battery. So I'll go ahead and write my drops on the left side here. So I've got a 12-volt drop. I'll keep walking, and I have a jump across the 3 ohm resistor. So I'll put I3 and then 3 here, 3 ohm resistor. Good so far? And so that's the bottom mesh. It's always good to note which one you're doing. And I'll go ahead and say the top mesh. So here, walking, I've got a 9-volt drop across one of those batteries. I keep walking, I walk. I've got a 12-volt jump. So that goes on the other side of the equation. So I've got a 12-volt jump, walking, and then I have a drop across that 1 ohm resistor. Okay, so I better put that on the left side of the equation. And so I have I1 times 1. Okay. Now, of course, you can see the answer. I mean, I3 has to be 4 amps. I1, yeah, I mean, you can sub and solve and see pretty quickly what the answers are here. Let's go ahead and, as good practice, I will go ahead and set up the matrix equation while we're at it. Okay. In fact, take a moment, pause, go at it. Okay. Now, sometimes, of course, again, as the circuits get more and more complicated, you can see the value in doing those matrix equations. Right now, I will just simply write these down and we'll invert it with the calculator again, just to see it. Okay, so standard form, this top equation is already in standard form. And similarly, the second equation is already in standard form. Okay. The third equation, I need to move the 9 over to the other side. And so I end up with something like 1, 0, 0. And I'll go ahead and write this in augmented matrix form. So this is 0, 12, and 3. Right? Okay, good. And so, sure, why don't we just pull up our trusty little calculator here? Go ahead and pull that up and move that so you can actually see it. Okay. And let's go ahead. We'll just go ahead and put in the entire augmented matrix, 3 rows and 4 columns. Okay. We have 1, 1. I'll use the keyboard here since I don't have any negative numbers to worry about. 0, 0, 3, and 12. And 1, 0, 0, and 3. There we go. And now I'll quit out of that. And let's tell the calculator, our handy dandy calculator, that we want to do a reduced row echelon form, RF. So we'll do that and we'll specify matrix A and we'll let it work its magic. Boom. There we go. So we see at the end of the day, and again, you get the same thing if we did the inversion and the matrix multiplication, but we see at the end of the day that we have I1, I2, and I3. No, I'm sorry, I'll pull up that calculator again. We see that I1 is 3 amps, I2 is -7, and I3 is 4 amps. So we have something that says, hey, this is 3, -7, and 4. Ta-da! And again, note the presence of the negative sign. That just simply means that I2 is not going into the positive terminal of the 12-volt battery, but rather out of. Not surprising. And we're done. I guess we better label this. This is amps, technically. Now that being said, let's go ahead and I'll swap to another page. Let's go ahead and keep the direction of our currents and see what happens if we use the sign conventions, the passive sign conventions, to double check and see if the power is balanced. All right, let's go ahead and let's make sure that our powers are also balanced. In other words, we should see that the summation of the powers is equal to 0 for everything, all of the elements. Okay. So first of all, I'm going to do it based on the directions that we arbitrarily chose for our solving of the circuit in the first place. So let's go ahead. Now we have 1, 2, 3, 4 circuit elements. So we better make sure that we have 4 elements in our summation. So I'll go ahead and say the power of the 9-volt. We have the power of the 12-volt battery. We have the power of the 1-ohm resistor, and the power of the 3-ohm resistor equals 0. Okay. And maybe I should put a question mark here, right? We're trying to verify that this is indeed the case based on our solution. Okay. Now let's go through. For the 9-volt battery, we chose the current to run into the positive terminal. And by the passive sign convention, that means the power should be positive. Okay, good. So we have 3 amps, I1, running into the 9-volt battery. And again, recall, I'm using the idea that the power is given by the current times the potential drop across the element. So for the next one, same idea. We have current I2, which is given as -7, times the 12-volt battery. Okay. And notice again that based on the direction we chose, that current is going into the positive terminal. So I'm keeping the positive sign in front of that term. Let's go ahead, next one. Now we go to resistor 1, and we see that the current is entering the positive resistor, or the positive side of the resistor. So I'm going to keep that positive sign. And the current is 3 amps. The resistance is 1 ohm. And keep in mind now, for the resistor, I'm going to use this idea that the potential drop across the resistor is given by IR. Okay. So I need to square the current and multiply by the resistance. Same idea for I3. Again, it's entering the high side, so I keep that positive sign. I3 is a value of 4 amps, and I have a resistance of 3. And the question is, does that whole thing equal 0? Get rid of those. Well, let's go ahead. We have 27 minus 84 plus 9 plus 48. 16 times 3, 48. Does that whole rigmarole equal 0? Well, 27, 36, that would be 54, 84. Ah, good, good, good. So indeed, we find out, as we should, that the power is balanced. Nice. Well, let's make sure. Let's really convince ourselves that we're okay here. Okay? Let's say for a second that we said, okay, we don't like the fact that this is a negative sign, that current there. Let's go ahead and redraw the circuit with the currents in the proper direction. Good. And again, we can double check now as to whether the sum of the powers is going to still be 0. Now, as we go through and we look, you notice that I have changed the direction of I2. And so in this, I'll put this as actual, okay? Whereas this is kind of the model, how we solved it. So I've drawn I2 running in the opposite direction. That means that I2 should now be equal to 7 amps, so positive value. But because of that, notice that now, when I'm thinking about the power of the 12-volt battery, because I've changed the direction of I2, I have lost the negative sign. But at the same time, now the current enters the negative terminal of the battery, not the positive terminal as was the case, or the case when I was actually modeling the system. And so although I no longer have the negative sign on the current, the passive sign convention tells me now I pick up a negative sign in front of everything. So I would write a positive current times the potential of the battery, and the negative sign will come from the passive sign convention. And so, although you can double check with everything else that we've done in terms of the rest of the stuff, that's the only thing that changes. I flipped I2, that drops the negative sign from the current, but picks up the negative sign from the passive sign convention. So that balances out, it works out for us. Pretty cool, huh? Sweet. Okay, so I thought, okay, another example. I'm just going to pull one from the book. I'm just going to take a screenshot of one of the problems from the book and figure, let's just work through it. Just a minute here. Alrighty then. So I just snitched a problem 249 out of the book. And yeah, let's go ahead and find the current. It's asking for the current running from the battery. We could probably just find the current through all of the resistive elements. So go ahead, take a minute, see if you can at least get to the point where you write down all of the equations. Got it? Sweet. Well, let's go ahead. We are off and running. Instead of highlighting the nodes and the essential nodes, I'm going to start labeling them. That's just simply just to keep the figure looking a little bit cleaner. So we notice that we're going to have some nodes. We have a node here, an essential node, I should say. We're going to have a second one here. I'll call that one B. Now you notice this long line here, this perfect wire. So right there, I'll call that one C. And although I could label the fourth one anywhere I want on the bottom, I'll just label it right here as D as in dog. Okay? Bear in mind that that whole segment beneath at the bottom is one node. Okay, well, let's rock and roll. We have the number of essential nodes. We see that that is 4, unless I missed something. And so we should probably count up the number of essential branches as well. This will tell us how many currents we actually need to find. So we have 1, 2, 3, 4, 5, 6, and 7. So it looks like we have 7. And why don't we, while we're at it, go ahead and draw in those. So we have I. I'll call this one I1. Call that I2. This one I3. We have I4, I5, and I6. There we go. Rock and roll. So we should probably label the high and low sides. And like I said, as you start getting more and more familiar and more comfortable with this, you might end up skipping a couple of steps or combining several steps. So that's high and low. Okay, but for right now, convince me that you know exactly what you're doing. So it's always good to follow all the steps. And now we're at the point where we can apply KCL. Okay? Now we notice that here, the number of essential nodes is 4, and so we can use Kirchhoff's current law to get 3 of those equations. Okay? So I'll go ahead, I'm going to choose node A, I'll choose node B, and I'll choose node C. Those are the 3 nodes where I'll get my equations from. So node A, I notice I have I coming in, and I have chosen I1 and I4 to be going out. So there's 1. For the second one, B, I have I1 going in, and I have I2 and I3 going out. So there we go with that one. Last one, I chose node C, where I have I4 going in, and I have I5 and I6 going out. There we go. So we have 3 of our 7 equations. So we will need to use KVL, Kirchhoff's voltage law, to get the other 4 equations. Well, why not? I will go ahead, let me mark these up here. I will go ahead and use the leftmost mesh, and I'll just work my way inwards. So I'll use, excuse me, that's ugly, but okay. And then I'll go ahead and use this small one right here. So I tend to, I'll use the smaller meshes, if you will. So starting from the leftmost one, and I'll just work my way to the right, I'll go ahead. So leftmost one, I see a jump. I go across the 30 ohm resistor, and I see a jump. So I'll put I3 here. Keep going. I see a jump when I hit the 10 ohm resistor. And I keep going. Now I see a drop when I hit the 60 ohm resistor. So I'll put the 60 on the other side, and that is multiplied by I2. Next one. Okay. So I'll go to the next one. I'm going to start in the lower left-hand corner again. I jump across 60, so I have a 60 times I2. That's my jump. I have another jump of 40 I1. And then I have a third jump, 5 times I. Keep going, keep going, keep going. Jump, jump, jump. Oh, I have a drop. Okay, there we go. So, and then I have a drop of 50 volts. Okay, the third mesh, I will start and I have a jump of 50. Keep going, I have a drop of 5. Okay, well, I've been using the right-hand side for the drops. So I'll put 5I in there. I have another drop of 25, so I'll put plus 25 I4. Keep going, keep going, keep going. Another drop. So I have another drop of 10 I5. And we're back at our starting spot. Last one, I'll start in the lower left-hand corner again. I have a jump of 10. So put 10 I5. And then I have a drop of 10 I6. And now we have all of our equations that we need. That should be sufficient. Now let's go ahead and solve. And again, this is where the power of that matrix multiplication, that matrix stuff comes into play. So if I write these in standard form, let me go ahead. I'll write in the variable matrix. So I1, I2, excuse me, I1, I2, I3, I4, I5, and I6. I usually write in that variable matrix first, just to remind myself which column represents which variable. Okay. So now let's go ahead and write in the coefficient matrix. And I'm just going to go and just write down all 7 of these equations. So for the coefficient matrix, for the first equation, and remember, I need to get this in standard form, so these 2 have to get moved to the other side of the equation. I have 1, negative 1, I2, I3, negative I4, I5, I6. And that whole rigmarole is going to be equal to 0. Second one, I have 0i, and then I have I1, negative I2, negative I3, 0, 0, 0. And then again, that whole thing is equal to 0. You can see why KCL, the Kirchhoff's current law, is really helpful, is because all of the coefficients are either 1 or negative 1. Maybe I should say 1, negative 1, and 0. So it's a little simpler when you write it. Third one, well, I have 0i, 0, 1, 2, 3. I have I4, negative I5, negative I6, and that whole rigmarole is 0 again. So that's it for Kirchhoff's current law. Now we have to do the voltage law. Bummer. So I1, I'll go ahead and move I2 to the other side. So I have negative 60. Then I have 10I3. Uh-oh. It seems that I've used oh no, okay. Excuse me, I3 appears twice in that equation. So I have 10I3 and 30I3, so I should write 40I3. And then I have 0, 0, 0, and again, 0. Next one, right here, we have 5I1, 5I, 40I1. That's an ugly 40, we'll do that again. We have 60I2, 0I3, no I4, no I5, no I6. And now here we have to be careful. We do have that 50. So for the first time, I have 50 instead of a 0. How many equations? 1, 2, 3, 4, 5. So we're down to equation 6, which is already in standard form. So I have 50. Okay. And again, 5, no I1, no I2, no I3. 25, I4, 10, I5, and 0, I6. And then the last one, 2, 3, 4, we have 10, I5, and negative 10, I6. And so now we have successfully written our coefficient matrix. We have our B matrix, if you will. And now we sub and solve. Now let's do it on the calculator, of course. There we go. So again, we'll have to do a little bit. So again, matrix. Oops, excuse me. Let's clear everything. Let's do our matrix and we'll edit. And this one is going to be a 7 by 8 matrix. 8. Okay, enter. Okay, so it seems like it can still handle a 7 by 8 matrix. So let's go ahead. Let's go and we'll enter in everything. And I'm just going to follow what I have here. Good. Awesome. Now we'll just work our little magic here. Math. B. There we go. And we'll have it work its magic. And while we're at it, I'm going to tell it to express the final answer as fractions. Okay. There we go. A little harder to look at, right? But this last column that we have should give us the final answers. There we go. And you can see they're not going to be nice numbers. So what we have, oops, excuse me, I'll just leave it like that. Okay. I don't think we need to rewrite it, but we have I1, which is slightly more than 1, et cetera, et cetera. And you notice again that we don't have any negative values, so we have clearly chosen the proper direction for everything. Another sanity check, we notice that down here, highlight, you notice that those two resistors are the same, and so we would expect the current running through both of those resistors to be the same. Okay. Sweet, huh? Cool. I will leave it to you, but go ahead and power check it while you're at it. Okay, good. Sweet. Why don't we pick up one more, and then we'll call it quits for the day. So let me go ahead and raser la table and get another problem. Be right back. All right, well, we tried a circuit that had multiple potential sources in it. Why don't we try one with some current sources in it? So here's another problem for you. And yeah, go ahead, take it in for a minute, and let's again see if we can determine the current flowing through each of the resistors. Got a stab at it? Sweet, let's go at it. Okay, well, I will go through, and first of all, let's go ahead and label some nodes here. So it looks like we have a node there. We have an essential node here. I'll call that one B, as in boy. Looks like we have a third one here, Charlie, and Delta. So we have Alpha, Bravo, Charlie, and Delta. And yeah, that looks like it's it. So we have 4 essential nodes. Okay. Let's go ahead and think about how many essential branches do we have. Looks like we have 8. Right, there's 2 paths connecting each essential node. So we actually have 8 essential branches. Right? Now the upshot here, one of the cool things about that is that we notice that although we have 8 essential branches, we know the current in 4 of those essential branches due to the current sources. Always helpful. Okay. So, namely, these current sources, if we go back and look, when we have potential sources, batteries, for example, you notice that those play a role when we apply KVL, Kirchhoff's voltage law. Here, because we have these current sources, we will see their influence in when we apply KCL, Kirchhoff's current laws. Okay? So that's one thing to notice. The other thing to notice is if we wanted to analyze this circuit completely, the thing that we do not know are the voltage drops. We don't know what voltage drops are required across these elements. Okay? So 4 of the unknowns that we will have to find are the currents through each of the resistors in that diamond shape. And the other 4 unknowns that we'll need to find, let's go ahead and find everything, are the potential drops across these current supplies. Okay? So just bear that in mind where those come in at. Okay, so KCL. We have established that we have 4 nodes, essential nodes, which means we can use 3 equations. Okay, well, let's back step here. Excuse me, I have already jumped over. Let's see, well, this goes in. Let's go ahead and I'll call that I1. We'll call that one I2. Right here, I'll call this I3. And yeah, why not? We'll call that one I4. So just getting some directions in there. Let's go ahead and label high and low sides. So we have a high side and a low side. High and low. High and low. Go ahead, take a minute. See if you can write down some equations for KCL. Got it? Sweet. Okay, here we go. So I will go ahead. I'll use essential node A, B, and C. And just chose the 3. Alphabetical order. Very creative. And so what do I see? Well, I have 2 amps going in from the upper left current supply, and I have 2 amps going out from the upper right current supply. So I'll go ahead. Let's see. I have 2 amps going in, and that equals I1 plus I2 plus the 2 amps going out. How about for B? Well, I have 2 amps going in plus I1. So I have 2 plus I1 going in. And let's see. Oh, excuse me. I have a 5 as well. 5 plus 5. And I have I3 going out. How about C? Well, C, I have 2.5 going in plus I4 and I3 as I have it drawn. So I have I3 plus I4. And going out, I have my full 5 amps. There we go. And that's all she wrote for those 3. That's all I can do for KCL. Okay. I'll go over here and write this for KVL. So now I need to apply KVL. Okay. And I'll need to do another 5 equations for KVL. Okay. No way around it. Okay. So what will I do? Let's go ahead and sure. We'll see if we can get creative here. I'm going to let's do the 4 corner triangles. And again, I will do these in clockwise fashion. So I'll do them all in clockwise fashion. And although I did not label the high and low sides for the potential or the current sources, let's go ahead and do that now. Okay. So I'll call this the high side, and I'll call that the low side. So we'll say that it goes from the high side to the low side, high side to low, high side to low side. There we go. Okay. So let's go ahead. I'll start with the lower left triangle, and I'll walk around. And we notice that we have a jump. I'll call that the potential jump of the 2.5 source. I'll have to figure out something better than that. Okay, so we have that, and then we have a drop. We have I4 times the 4 ohm source. And then we're back to the beginning again. So we're done. Sweet. How about the upper left? Well, I have a drop of the 2 amp source, so I'll put V of 2 amps. Keep going around. I have a drop of the 4 ohm, so I get plus 4 I2, and that will equal 0. Third one, I'll do upper right, and I have a drop of 2 amps. I'll call it the right one, and this one is the left one. Okay. And then I have a jump, so I have a drop of the 2 amp source, and I have a jump over the 2 ohm source. So that would be 2 I1. Excuse me, I've been I1 times 2. And how about this bottom left one? I have a jump on the 2 ohm source, and I have a jump on the 5 amp source. So I'll say the potential of 5 amp source plus 2 times I3. And for kicks, we need one more, or one shy. I'll go ahead and just do that center diamond clockwise. So here we go. If I start at, I don't know, C, I have a jump of 4. So I have I4 times 4. I have another jump of I2 times 4. I have a drop of I1 times 2. And I have another drop of I3 times 2. Let's go ahead and get these into standard form first. Should have done that first. So we'll go ahead and write down our coefficient matrix. So I'll use this top upper right spot. And again, what I'll do is I'll use I1, I2, I3, I4. Then I'll do the potential for the 2.5 amp source. I'll do the potential for this 2 amp source upper left, the potential for the 2 amp source upper right, and the potential for the 5 amp source. Okay. And this is perfectly valid because we're dealing with linear equations. You don't have to have just all currents or all potentials. You can have some sort of mix between these as well. So let's go ahead. We'll just start with this KCL. And what we have is 0. And we notice that it's a 1, 1 based on the order, and then zeros for the rest of it. And rather than writing the other 6 zeros, I'll just put 0 there. Okay, that's not a good way to do it. I should write 6 zeros. 1, 2, 3, 4, 5, and 6. Okay. Second one. Well, I have the 1, I1, no I2, a negative I3, and then the rest of these are 0. And then I better move the 2 and the 5 to the other side. So I get a negative 3. Third one, I have 0, 0, 1, 1, 0, 0, 0, 0, and I move the 2.5 to the other side, and so I get 2.5. Good? KVL. Alrighty. Well, I need to get standard form, so I'll go ahead and move the 2.5 to the other side. And so I have 0, 0, this is I4, the 4th position. The 5th position is my voltage, so I'll put a negative 1, 0, 0, 0, and that whole thing is equal to 0. Okay. Here, 4, so I have 0, I2 has a coefficient of 4, 0, 0, 0. Now my 5th position is the voltage 2. So I'll put 0, 0. There we go. And this whole thing is equal to 0. So you see, you have to be a little disciplined when you're writing down your equations here. Okay, so our coefficient for I1 is 2. 0, 0, 0, 0, 0, and negative 1, 0. We have a 0 there. Okay, I5 is the last one. So we have I1, I2, coefficient of I3, and then we have I5 at the very end, and that one's 0. And lastly, this one we got to be careful. I will go ahead and move these two over to the other side. And so what we have is 2, negative 4, 2, negative 4, don't drop that negative sign, and then zeros for the rest of the time. And that whole thing equals 0. Sehr gut, sehr gut, sehr gut. All right. So let's go ahead. Let's queue up MATLAB and find the answer. Okay, so I've got MATLAB queued up here. And just for completeness, let's go ahead and work on how to form a matrix in MATLAB. So again, I'm just going to call the coefficient matrix A. And so I'll put equals in here. Now MATLAB makes a distinction between the round brackets, the square bracket, and the curly bracket. Okay, so you need to be aware of that. If I want a matrix, I use the square bracket. Okay. Now, by the magic of fast forwarding, I'll go ahead and type in our matrix here. You can separate elements of a row by either using a comma, or if you prefer, if it's faster, you can just use a space. So I will go ahead and use a space. Is that 8, 2, 4, 6, 8? Yes. Okay. Now, to separate rows, you use a semicolon. So I have put in the first row, each element separated by spaces and or a comma. And then to go to the next row, I'll use a semicolon. So let's go ahead. Good. Now it's always good to double check that everything matches up fine. Okay, so it's you fat finger typo or you get off by one element. So I am just checking with my notes here. I've got a screenshot of the matrix on the other side. So that's usually the biggest place where mistakes arise. Okay, let's go ahead and put our B matrix in. B matrix, a little harder. That semicolon doesn't quite roll off the fingers. There we go. 2, 4, 6, 7. My B matrix is not large enough. I missed one. There we go. Okay. So now we're all set. Let's go ahead and do the inverse of A times B. Boom. There we go. And if we want, let's go ahead, inverse. We can get this as rationals. You can see that it's related to 3. So you see a lot of 0.666. You see a lot of 0.33s. So a lot of these are 1/3 of some sort. There we go. And boom, we're done. Now notice, okay, so first of all, 2 things I will point out to you. First is that notice how all 4 of the potential drops across the current sources are negative. So what does that mean about how I labeled those? Yeah, I did them backwards, right? I said, okay, well, I'll say the arrowhead is the positive side, the arrow tail is the negative side. Is that how I did it? I can't remember, but I've labeled them backwards. Okay, so note that first of all. And because I consistently labeled all 4 current sources the same way, okay, then all 4 of those current sources have negative signs. Okay, no problem. That means I have to flip the plus and the negatives. Okay. The other thing to notice, okay, well, the same thing applies to the currents. I have 2 of my currents are in the wrong direction. Okay, current 1 and current 4. So I'd have to, theoretically, if I redrew the figure, I'd have to flip those 2 directions from how I had them. Okay. That's okay. We understand what these negative signs mean. Okay. Cool. Well, I think that's all for this video. I think I'll post another one. We'll do some more examples, but I think this one got long enough. Thanks for your attention. I'll see you next time.